system. Dr. Leal received in electrical engineering a PhD degree from the Federal University of Para in 2018. From 2016 to 2017, he was a visiting research scholar at the University of Florida in Gainesville. Then he was an assistant professor at the Federal University of Para, and since 2022, he has been an assistant professor at New Mexico Tech, US, and an active researcher at Lumen Lab. Aldous, the floor is yours.
Thank you, Professor Nucci. Good afternoon, everyone. So maybe that's like the more easy presentation for today. I'm gonna try to show some results about some experiments that we are trying to revisit. So that's the outline for my presentation. I'm gonna talk a brief introduction, data methodology, results, and discussion, and finally the summary. Okay, introduction. So according to most of the international standards for lightning protection, they do not distinguish between sharp and blunt air terminals or lightning rods, right? But when you go to the market, everywhere, what the type of terminal that you're going to find is the sharp or pointed terminal, right? However, about 30 years ago, the Wemhoner group developed a very extensive research on lightning rods. So they deploy a competition between blunt and sharp rods around the Magdalena Mountains and the Langer Lab, and over 7 years, no sharp rod was struck by lightning. All the time, the lightning struck the blunt rod. Okay, so that was one of the motivations to revisit that topic. Also, during like the same period, the same research, they found that when the leader approaches the ground, the sharp rod emits current, right? But not the blunt one, as we can see here. So we can see some emissions from the sharp, but we cannot see from the blunt, just after the return stroke. So on the time of the return stroke, we see current on both, okay? And now we are revisit the same topic, but we are including more data. So we are still measuring the currents on the rods. We put the lightning rods to compete again, but now we have like more like modern lightning location system. We have LMA, so we can see where is the lightning source. We have also electric field mill, so we know the intensity of the ambient field, and lightning location system data, include Earth Networks data, in which we have the reported peak current, the lightning type, and a precise location. Okay, so let's move to the methodology of this work. So here are the 2 lightning rods that we installed, that we deploy for a competition, sharp one and the blunt. So the lightning rods were deployed at the top of the highest peak in New Mexico, so about 300 meters above sea level. So here is South Body, and at the top of the South Body peak we have the Kiva 2. So Kiva 2, it's a kind of bunker, so in which we install the 6 high lightning rods, and they are like 6 meters apart, so there is like no interference between the 2 rods. And here is the electric field sensor, and it's not in the picture, the electric field meter is about here. So the digitized system that we use like to record the currents has like a bandwidth of 500 kilohertz, 16 bits, and also we include electric field mill data, LMA, and lightning location data. So let's move to the results. So first, we characterize our results in 3 types. So the first one, both the sharp and the blunt emitted currents during the step leader. So that's one example. So we have both emitting currents during the step leader and at the return stroke. The second scenario, both rods emit current during the return stroke phase, but only the sharp rod continues to emit current. So here we can see the blunt and the sharp one. And finally, the sharp rod emit current during the leader phase, during the return stroke phase, and after the return stroke. Okay, so let's move to our table here. So we recorded about 10 lightning flashes last summer, 2023. And as we can see here, just one was in the first scenario. Most of them were in the second scenario, right? In which we have lightning current emissions during the return stroke phase. As we can see in this table here, most of our flashes were positive. Just one was negative. So that information caught our attention. So using LMA, we characterize the charge centers for the thunderstorms, and we realized very large positive charge centers in the thunderstorm. So that's maybe why that specific thunderstorm produced a lot of positive flashes. Okay, and just to put everyone on the same page here about the results. So when I say that upward positive streamer or upward positive currents flowing from our rods, the currents in our measurements are negative. So we have like upward positive charge going up, so we have this type of measurements. Or when we have positive charge going down or negative charge going up, we have this type of measurements. The peak current is going up. So it's always confusing when we try to measure currents from lightning, because we have to establish a path for the electrons or for the positive charge. So in that picture, we make sure that everyone is in the same page. Okay, so let's show some results for some flashes. So here is one flash that had many subsequent return strokes, but the lightning rods respond only to the first return stroke, which we can see here in more details. So the Sharpie rod respond about 0.46 milliseconds before the blunt, and that is a negative return stroke. Okay, so we have the leader approaching the ground here, and then boom, the return stroke. So during the leader phase, we can see the current emissions from both rods, but the sharp starts emitting first. And here are the LNA, so that's the 3D propagation for that specific lightning flash. So that's one positive flash here, okay? At this example, the lightning rod responds only after the return stroke. We have like a big positive electric field change, and then both starts to doing lightning emissions. So that's the propagation for the positive one. We can see that the horizontal propagation is huge, about 60 kilometers. And another example here, so that's another interesting example. The blunt lightning rod respond at the same time in the return stroke, but the sharp starts to respond about 200 milliseconds before. So maybe here it's a intra-cloud process, or maybe a leader trying to develop towards the ground, and the sharp rod starts responding at this point here and also before. So we can see that the electric field change is about 25 kilovolts per meter at that time. And finally, in summary, we have figured out some interesting conclusions. So most of the time, the sharp rod record the currents before the blunt one. So 9 out of 10. And when the blunt detects first we can say that it was at the same time, because it was just a few microseconds first. The early streamer emission may cause weakening of the electric field around the tips of the sharp rod. So what we understand here, and we have done some calculations of, also we can see in the literature, is that when the sharp lightning rod starts to emit current first, it shields itself. So it's not good for lightning protection, because when the leader is approaching the lightning rod, what happened is that at the tip of the sharp rod, the electric field is not strong enough to launch long upward leaders. So that's why the blunt sometimes wins the competition. Third, the upward spikes visible in almost every lightning rod that I show here, they are positive streamers. And they were more common than negative streamers. So we record just one time negative streamers, as I showed in one of the examples. So these apparent polarity asymmetry makes sense because the launch positive streamers is kind of easier than launch negative streamers. And that's one of the differences from the past studies for this current study here, because in the past they measure only for negative flashes, and here I show for positive as well. So perhaps lightning protection systems are mostly designed for negative flashes, but they can, maybe we need to investigate more if the efficiency for lightning protections for negative flashes are the same as for positive flashes. So that's why more studies are needed to investigate how lightning polarity is related to the shape of the lightning rod. So thank you for your attention, and I'm open for questions.
Thank you. We have time for comments or questions.
Thank you for the presentation. I was very involved with Charlie Moore in the initial study, so this is very interesting. I appreciate the effort. It looked like to me, did you have only one each negative and one each positive? Excuse me, one sharp and one blunt.
Yes.
Air terminals.
Yeah.
And when those were located on poles rather than a lower than they were initially, do you think that makes a difference?
So the pole, we have a pole, and the pole is like we have insulators. So we have the pole, we have insulators, and then we have a ground wiring connected to the rods all the way to the ground.
Yeah.
So the pole is not connected to the rods. So that's
right. I just mean the fact that it was higher in elevation. I mean, you're already on the mountain, and then it's even higher. Just a question.
Yeah, that's a good point. Maybe this summer or next summer we can try to deploy both rods at ground level and see what happens. Yeah.
And thank you.
Thank you.
Thank you for the information. About the wind speed and wind direction, is there also information to see the wind comes from the right side, or is it to the sharp one, or which speed they have? Because it's important, I think.
Yeah. That's we have never thought about that, but maybe in the future we can try to address the wind direction and the wind speed.
Yeah, thank you.
Yeah, Carl Tomaso, Center for Language Solutions. Thanks. Interesting presentation. The question that I have is, I believe that you stated in the presentation that the analog bandwidth of the current sensor that you're using is 500 kilohertz. And I was wondering if you've done FFT analysis on those wave shapes that you have reported to see what the bandwidth of the current that you're measuring is, and see if you might need perhaps a little higher bandwidth current sensor to be able to resolve those current wave shapes.
Yeah, so that was the instrument that we had available past summer. This summer we have upgrades to 10 megahertz but we have done any like frequency analysis yet, but we can do in the future.
Thank you, Derek.
Hi, everyone. My name is from Brazil. Nice presentation, thank you. I have one doubt concerning your summary. Your summary, you said that most of the events were positive. Yes, you said 9 of 10 were positive.
Yes, yes.
So we presumably the an upward event would be negative, okay? Upward limit if you do. And how you say in the third conclusion that what was visible were positive spikes and not the negative?
Okay. We'll go back here. So when a negative flash happens, we have a negative step leader approaching the ground, so we have this situation. So at this situation, the positive charges are going upwards, so positive streamers. So, and we detect the current emissions during the leader phase only for the negative flash, but never for positive flash. Because positive flashes, we have the other situation. We have like a positive leader approaching the ground. So we have, we must have like negative streamers going up. And we never measured that situation here. So that's why we always measure like current emissions for positive flashes after the return stroke.
Okay.
So just after the return stroke, we have like negative charges above the
It's
rods.
clear. Thank you.
Yeah.